Assalamualaikum warahmatullahi wabarakatuh and good morning everyone. Today I will present about topic electric current and direct current circuits for subtopic 3.4 electromotive force, internal resistance and potential difference. Electromotive force or EMF. Electromotive force is defined as the energy provided by the source, which means battery or cell, to its unit charge that flows through the external and internal resistance. There are two formulas used for this topic. First, V is equal EMF minus I small r. The second one is EMF is equal to I multiplied by capital R plus small r. The unit for EMF is volt, same as potential difference. This is the illustration for circuit. Next, we will watch a video on how electromotive force works.
EMF, or electromotive force, refers to the voltage created by a battery or by a changing magnetic field. Counter EMF, also called back EMF, is a related phenomenon that we will illustrate in this animation. Here is a simple circuit featuring a battery, a knife switch, and a light bulb. This circuit also contains a wire coil that serves as an inductor. Inductors store energy in the form of magnetic fields that are generated around them when a current passes through them. They are called inductors because they induce a voltage in their coils when that magnetic field changes. We will see this in a minute. The elements in this animation are not represented to scale, and the action we will show in super slow motion actually takes place in the blink of an eye. But this animation is helpful for illustrating how back EMF works. When we power this circuit, the electrons in the current create a magnetic field around the wire as they move through it, as shown by these blue arrows. If the wire is formed into a coil, like this inductor, the magnetic field lines converge in the center. They gradually build up to a maximum magnetic field that is much stronger than the one around the straight length of the wire. Let's watch this again, but this time we'll pay closer attention to what's happening in the wire conductor. In this parallel circuit, the current can travel either through the inductor or through the light bulb. When the current reaches this junction, it splits and flows to both the inductor and to the light bulb. At first, the current flows much more strongly towards the light bulb. This happens because as the magnetic field in the inductor grows, it induces its own voltage through Faraday's law. This is called electromagnetic induction. So the inductor here is creating a back EMF represented by this yellow arrow. Back EMF always opposes the change that created it. So in this instance, the back EMF is opposing the change created by turning on the circuit. It opposes the current. The result, as you can see, is that the back EMF effectively diverts the current away from the inductor and toward the light bulb. This causes the bulb to light up, but only briefly. Once the magnetic field around the inductor reaches its maximum field, the back EMF fades, and the current now favors the path through the inductor because the bulb creates some resistance to the current. The same phenomenon occurs when the magnetic field is shrinking. which happens when we open the switch and stop current flow from the battery. Once again, the back EMF opposes the change that created it. In this case, the change is the cessation of current. So, opposing this change, the back EMF wants to maintain the current, which flows once again to the bulb, causing it to flash before it fades away altogether.
This our problem. Next, my group mate will explain about terminal potential difference and internal resistance.
Hello everyone, so today I would like to explain to you about terminal potential difference, or the other name is terminal voltage. Okay, the unit used for terminal voltage is volt. The definition of terminal voltage is work done in bringing a unit of test charge from negative to positive terminal through external resistance only. Okay, the value of V equals to electromotive force, or EMF, when there is no current flowing. This means if our EMF is 6 volt and the I is equals to 0, so our value of terminal voltage will equals to 6 volt, same as the value of electromotive force, EMF. How to calculate terminal voltage? Okay, terminal voltage equals to EMF minus current times internal resistance. Okay, current times internal resistance is voltage drop in internal resistance. Next is on how to calculate current if we are given EMF, resistance, and internal resistance. Okay, current I equals to EMF over resistance plus internal resistance. So here we take both value of resistance and also internal resistance. Okay, after calculating, the value of our terminal voltage should be smaller than EMF because of internal resistance. When we calculate the terminal voltage, as you can see here, we take into consideration the internal resistance. So the value of terminal voltage should be smaller than our value of EMF. Okay, so now I would like to show you a question on how to use the equations I just showed you just now. Okay, the question says a 12 volt battery has an internal resistance of 1.5 ohm and is connected to a 6.0 ohm resistor. So 12 volt is our EMF and 1.5 is our internal resistance, the small r, and the 6.0 ohm is our resistor, big R. Okay. The first question is, what is the current in the circuit? Okay. How to calculate this is, I will use the equation I equals to EMF over R plus small r. Okay, so after that, we just substitute the value. So our EMF is 12 volt. Our internal resistance is 1.5 ohm and our resistance is 6.0 ohm. So after calculate, we will get our current equals to 1.6 ampere. The next question is, what is the terminal voltage of the battery? So here I will use the equation terminal voltage equals to EMF minus current times internal resistance. So here our EMF is same, 12 volt, minus 1.6 ampere, the value we get from question 1, times 1.5 ohm, our internal resistance. After calculating, we will get our terminal voltage will be equals to 9.6 volt. Okay, 9.6 volt is smaller than 12 volt. So this shows that our terminal voltage will be definitely smaller than our EMF. So I think that's all from me. Thank you.
Assalamualaikum and hi to everyone. Hari ini saya akan terangkan tentang internal resistance. Internal resistance is defined as the resistance of the chemicals inside the battery, which is cell, between the poles. The smaller the internal resistance for a given EMF, the more current and the more power the source battery can supply. Secondly, internal resistance can behave in complex ways. As note, R increases as a battery is depleted and electrolyte wears out. Internal resistance may also depend on the magnitude and direction of the current through a voltage source, its temperature, and type of chemical material in the battery. The internal resistance of rechargeable nickel-cadmium cells, for example, depends on how many times and how deeply they have been depleted. So, since internal resistance depends on magnitude and direction, kita boleh nampak dekat figure 1 ni, internal resistance dekat terminal positif, yang dekat figure 2 ni, internal resistance at terminal negatif. So, ni adalah dua contoh figure symbol of EMF and internal resistance in the electrical circuit. So, we move on to the tutorial question. Soalan dia, soalan 6. Dia kata figure 3.2 show a battery BMF 12 volt and internal resistance R equal to 2 ohm is connected to a resistor R equal to 4 ohm. Kita boleh tengok dekat figure 3.2 ni. Ni contoh figure dia. So A, dia kata what is the reading of ammeter and voltmeter in the circuit. Soalan B, when resistor of 4 ohm is replaced by a conductor of 0 resistance, what is the new reading of the ammeter and voltmeter? Okay, kita buat soalan A dulu. A dia kata what is the reading of ammeter and voltmeter in the circuit. So, dia dah bagi EMF equal to 12 volt. Internal resistance dia kasih 2 ohm. Dengan resistor equal to 4 ohm. So, senang dia. Kita nak cari voltmeter and ammeter in the circuit. Kita guna dulu formula EMF. EMF equal to I R besar plus I R kecil. So, masukkan je EMF equal to 12 equal to I darab 4 plus I darab 2. Sebab dia dah kasih kat sini, dia dah kasih kat soalan. So kita akan dapat I equal to 2 ampere. Bila dah dapat I ni, kita terus masukkan dalam formula V equal to IR. So senang je lah, masukkan je dalam formula I dah kita dah dapat 2 ampere. Masukkan 2. Resistor kita dapat 4 ohm, masukkan je. So 2 darab 4 jadi 8 volt. So, untuk soalan B pun senang juga sebab dia direct question. Dia dah kasih when resistor of 4 ohm is replaced by a conductor of 0 resistance. So, kita buatlah terus R equal to 0. What is the new reading of the ammeter and voltmeter? So, dengan cara yang sama, kita masukkan dalam formula EMF equal to I R besar plus I R kecil. Okay, kat tadi dia dah kasih EMF equal to 12, masukkan je dalam formula 12 equal to I darab 0. Sebab resistor yang baru ni dia kasih 0. Resistor. So, plus dengan I darab 2. So, kita akan dapat, ni dah boleh potong. So, kita akan dapat I equal to 6 ampere. So, next kita masukkan je macam tadi. Dalam formula V equal to IR. I kita dah dapat tadi 6 ampere. Masukkan 6. Resistor tadi dia kasih 0. So, 6 darab 0 jadi 0. So, 0 volt. Senang saja.